Swayam Prabha. Digital India. Educated India.
Okay, so I just wanted to complete this part of the exercise. This particular period of 45 minutes. Okay? So remember that we got the idea that an operator is represented as a matrix in terms of the two basis functions, alpha and beta. So if you put alpha here and beta here, you can see that this row is all alpha on the left side. If you put alpha here and if you put beta here, you see that it's all alpha in the column on the right and beta in the column on the right. This is the matrix representation of any operator using the base states, two basis functions. So it is alpha I plus alpha, alpha I plus beta, beta I plus alpha, beta I plus beta. This gives you this answer that Ix is 1 by 2 sigma x, which is the Pauli spin operator. Now, if you look at the Iz operator, you can see that Iz and alpha gives you half alpha. Therefore, if you have Iz here and alpha here, it gives you half alpha. So alpha is 1. So it gives you 1 by 2 here. Whereas Iz on beta gives you minus 1 by 2. You remember? Minus 1 by 2 beta. Therefore, if you write Iz beta here, alpha Iz beta gives you alpha minus 1 by 2 beta. That is the same. Okay? So you can see that the Iz operator has a matrix 1 by 2, 1, 0, 0, minus 1 off diagonal. This is the famous Pauli spin matrix Z component. You know who is this Pauli? This Pauli is the same man that you are all familiar in chemistry, the Pauli's exclusion principle, or the no two electrons can have all the 4 quantum numbers, the same chemistry. It's the same Pauli. Pauli was the first rigorous provider of the theory for the spin angular momentum. Iy has this form minus I by 2, I plus minus I minus on alpha. You remember I plus on alpha is 0. I minus on alpha gives you beta. There's a minus and a minus, so it gives you plus I by 2 beta. Okay? So Iy on alpha gives you I by 2 beta. Iy on beta gives you minus I by 2 alpha. You can see that here. I minus on beta is 0. I plus on beta gives you alpha. And there is a minus I by 2. So this is a minus I by 2 alpha. Therefore, you see Iy on alpha gives you beta. Iy on beta gives you alpha. So you can see that Iy on alpha gives you beta. This is 0. Iy on beta gives you alpha. Alpha is 1. So this part is non-zero. This part is non-zero. This part is 0. Iy is given by 1 by 2. This 1 by 2. 0 minus I 0. This is a famous Pauli spin matrix Y component. Okay? Now, the interesting thing is, I want you to verify this. You take the product of the matrix sigma x and sigma y, and you add it to the product of the matrix sigma y and sigma x, the answer is 0. They say, likewise, if you take the product of sigma x and sigma y, and take the product of sigma y and sigma x, but take the difference between the two, the answer you get is 2I sigma z. Therefore, the commutator sigma x comma sigma y is 2I sigma z. anti-commutator, instead of minus, it's plus. Anti-commutator is 0. So you can now add these two, sigma x, sigma y, sigma x, sigma y, sigma y. This goes away. So 2 sigma x, sigma y is 2I sigma z. So sigma x, sigma y is I sigma z. It's a famous relation between the Pauli spin matrix of x component and y component and the z component. Now you talked about x and y. You can do the same for y and z. You can do the same thing for z and x. So you can see that sigma y, sigma z plus sigma z, sigma y is 0. The matrices are all here. This is sigma x, 0, 1, 1, 0. Okay. Sigma y is 0 minus I 0. Sigma z, 1, 0, 0, minus 1. You have 3 matrices. These 3 matrices have this beautiful property that they anti-commute, and their commutator gives you the third matrix. You can see that sigma y, sigma z plus sigma z, sigma y is 0. Sigma y, sigma z minus sigma y, z, sigma y is 2I times sigma z, x. So if you add the 2, you get 2 sigma y, sigma z, and you get 2I sigma x, 2 cancels out. So you see sigma y, z is I sigma x. So x, y, z, cyclic, y, z, x, cyclic, z, x, y, cyclic. You can see that. Z, x, y, y, sigma y. So now the other thing is, if you take the square of the matrix, sigma x square, the answer you get is the identity matrix 1, 0, 0, 1. Take the square of sigma y square, you also get identity. Do the sigma z square, you also get the identity. Now, I want you to write these things down. I'll give you 5 minutes and verify these relations yourself. Write down these things. Sigma x is 0, 1, 1, 0. Sigma x. Okay. Sigma y is 0 minus I 0. This way. Sigma y. Okay. And sigma z is 1, 0, 0, minus 1. Sigma z. I want you to verify the following relations. This product. Sigma x, sigma y plus sigma y, sigma x is 0. Do the matrix multiplication. Add the 2. And then you do the reverse multiplication. AB, BA, 2 matrices. Same thing here. Sigma x, sigma y minus sigma y, sigma x. Show that what you get here is what you get when you do this multiplication. Likewise, this 2. Sigma y, sigma z plus sigma z, sigma y is 0. Verify this. Sigma y, sigma z minus sigma z, sigma y is equal to 2I sigma x. Verify this. Okay. If you verify these two, this is already verified because it's nothing but the sum of the 2. And the last one is sigma x, z, sigma x plus sigma x, sigma z is equal to 0. And write this down. Sigma z, sigma x minus sigma x, sigma z is 2I sigma y. Verify this. Okay? And also verify this one. Sigma x squared is equal to sigma y squared is equal to sigma z squared is equal to identity 1, 0, 0, 1 in matrix. Okay. So now comes the most important relationship in quantum mechanics and in the theory of angular momentum. The commutator of Ix and Iy is ix iy minus iy ix. The commutator is I iz. It's a fundamental relation. The commutator of y, z, you take x, y, z. You take y, z, you get x. You take z, x, you get y. So it's a cyclic permutation. X, y, z, x, y, z, x, y, z. So you can do the cyclic. Start any direction in the right direction, you get x and y gives you z, y and z gives you x, z and x gives you y. This can be written in the vector cross product notation. I cross I is equal to I times the vector I. This is quantum mechanical because in classical vectors, the cross product of a vector with itself is 0. A cross A is, you remember, A magnitude sine theta, the angle between the two. So if the vectors are parallel, the angle is 0. So classically, A cross A is 0. Classically, A dot A is A square. Okay? Here you can see I cross I is I. It's purely because the components do not commute with each other. So this commutation relation is the most fundamental relation among the components of angular momentum in 3 dimensions. Entire NMR, entire quantum mechanics of rotations, angular momentum, chemical reactions involving angular correlations, everything obeys this rule that one finds from quantum mechanics. And also you can verify that I square commutes with all 3 of them. I square commutes with Ix, I square commutes with Iy, I square commutes with Iz. But Ix and Iy do not commute. Ix and Iz do not commute. Iy and Iz do not commute. Okay. You can verify. You can see that I square comma Ix is Ix square plus Iy square plus Iz square comma Ix. So you can write Ix square comma Ix. This is 0. And you can verify this Iy square plus I comma Ix plus Iz square comma Ix. When you do the commutator is 0. How do you do the commutator? The commutator of this product AB comma C is A times the commutator of BC plus A comma C times the commutator of B. These things can be verified. Okay? So if you use this relation here, you will see that I square comma Ix is 0, I square comma Iy is 0, I square comma Iz is 0. Okay? So there is a lot of these things that you can verify. Go to spin 1. Okay? Spin 1 has 3 states, 1, 1, 1, 0, and 1 minus 1. So you can think of the matrix basis as 1, 1, 1, 0, 1 minus 1. And for the right-hand side, 1, 1, 1, 0, 1 minus 1. So we will have 9 elements. And you can calculate Ix as this matrix. I'll send you an assignment in which I show you how it is done. Okay? I'll show you this result. And likewise, the matrix Iy is given by this. The matrix for Iz is given by 1, 0, minus 1. So add this. Okay? Verify this. This means that you should verify this. Okay? Now, in spin 1, Ix, Iy, comma Iyx is not 0. Okay? In spin a half, sigma x, sigma y, it was 0. But Ix, Iy plus Iyx is not 0. Ix, Iz, Ix, that's also not 0. So you can calculate matrices for all these things using these matrices. Okay? And likewise, calculate the matrix for Iy square, calculate the matrix for Iz square. These are all problems that you should be able to do. and then determine matrix representations for the operators 3iz square minus I square, I plus square, I minus square, I plus iz and iz I plus sum, I minus iz and iz I minus sum. Okay? These operators are known by a special name called irreducible spherical tensor operators of rank 2. If you don't understand, don't worry, but you can calculate matrices using the matrix formula. Okay? So this is what is called the first leaf, the first page of the angular momentum book. Okay. Now, if you think that you find this, if this is the first time you are seeing, chances are 90% of you do not follow what is being said. Okay? It's not your problem. It's also my problem. I also, when I read something first time, if I don't understand, I don't throw that away. I keep on reading. Story படிக்கிற மாதிரி சில சமயத்தில் புரியாது, படிச்சுட்டே போங்க, திடீர்னு கொஞ்சம் மேலே போகணுன்னா ஒரு தடவை திருப்பி பார்ப்பீங்க, ஓ இதுதான் அவர் அந்த சொல்லியிருக்காரா அப்படின்னு. சரி, கொஞ்சம் வில் கோ ஆஃப்லைன். பொன்னியின் செல்வன் எத்தனை பேர் பார்த்தீங்க? பொன்னியின் செல்வன் எல்லாரும் பார்த்துருக்கீங்க. எல்லாருக்கும் அந்த கதை தெரியுமா? உங்களால் சொல்ல முடியுமா? படம் பார்த்துருக்கீங்க, அட்லீஸ்ட் படத்தில் சொல்கிற கதையாவது உங்களால் சொல்ல முடியுமா? புஸ்தகத்தை விடுக்கலாம், ஒரு தடவை பார்த்தா முடியுமா? முடியாது. என்னுடைய ஃப்ரெண்ட் ஒருத்தர் இருந்தார், இங்கே என் கூட படிச்சுட்டு இருந்தார். அவர் ஒரு எம்ஜிஆர் படத்தை குறைஞ்சது 40 தடவை பார்ப்பார். குறைஞ்சது கிட்டத்தட்ட 100 எம்ஜிஆர் படத்தையும் 40 4000 தேட்டருக்கு 4000 ஷோக்கு போயிருக்கார். எல்லா எம்ஜிஆர் படத்தையும் சீக்வன்ஷியலாக சொல்லுவார். எல்லா பாட்டையும் மனப்பாடமாக சொல்லுவார். I'm not saying you should read this 40 times, okay, to understand it. But இது புரியணும் அப்படின்னா you have to follow the problems. கொடுத்துருக்கிற ப்ராப்ளம்ஸை இதை வச்சு செய்ய முடியறதா, எனக்கு சொல்ல கொடுத்த மெத்தட் புரியுறதா அப்படிங்கிறத கவனிக்கணும். ஸோ குவாண்டம் மெக்கானிக்ஸ் cannot be understood by reading. Quantum mechanics is followed. You don't understand, you follow it and follow the mathematics if you solve a lot of problems. So problem solving is fundamental at the higher level. Master's level is the higher level. Bachelor's level is the introductory level. PUC and high school is the kids level, okay, where everything should be enjoyed. Go to BSc, you find something that you don't understand. In MSc, 90% of what you read, you will not understand first time. But you have to go and understand. My colleague, Prof. Damodaran, will give you 3 lectures on thermodynamics, on the principles of thermodynamics to you sooner, maybe next week. And if you think you already understood thermodynamics, just wait and listen to his lectures. Then you will know what you understood and what you didn't understand. Thermodynamics, you think that it's easy to understand. Quantum mechanics is very difficult to understand. Spectroscopy is even more difficult. And magnetic resonance, angular momentum, spin. Why are they teaching all these physics things to chemists? Because the whole damn thing is useful for chemists. You are able to do all your structural analysis using NMR spectroscopy. You are able to understand biology, a lot of biology, from NMR spectroscopy. You can get all the protein structures, all the amino acid structures beautifully from NMR spectroscopy. And these are all chemist objects. Therefore, the tool that you use, you must know how to use the tool. I have not even come to one-dimensional spectroscopy. I have not even talked to you about resonance. But resonance and one-dimensional spectroscopy are the most fundamental. I will probably take some other time, if there is a chance. Please, you also refer to the NPTEL site. There are lectures given by professors, chemistry and physics professors, on magnetic resonance spectroscopy. Please study them, listen to the lectures, and like stories, don't listen to them once, read them twice. Last question for you. How many of you read Kalki's Ponniyin Selvan? Kalki's Ponniyin Selvan is 5 volumes. Have you read it? எல்லாருக்கும் தமிழ் நல்லா தெரியும் இல்லையா? எல்லாருக்கும் தமிழ் நல்லா தெரியும். You know, we are studying physics, chemistry, biology with a lot of difficulty. You start reading Ponniyin Selvan novel, I bet you cannot put the book down. You won't be willing to put the book down. You want to finish it. So beautiful. I've read the book about 10 times, the 5 volumes. I've read Ponniyin Selvan about 10 times. And I can see from the first scene of Vandiyathevan coming from Yerikarai, from his Kanchi, he's coming to Tanjavur. The very last in the fifth volume, when Mangala dies in the arms of Vandiyathevan. I remember everything. Okay? But that's because when you read something, you have to get involved. You don't understand them, but you read them again. You do. In this case, Ponniyin Selvan, there is no problems to solve. It's a beautiful story. You remember some things first time, you remember more things second time, and as you read more and more, you remember the dialogues. The Tamil written in Ponniyin Selvan, Tamil language written in Ponniyin Selvan, is one of the most beautiful. We have such scholarly works, and now suddenly we are into the scholarly processes of science and technology. We have to understand. You have a fantastic opportunity for the next 20, 50 years or 70 years. If you continue to do science, the whole world is in front of you. All those things that I told you are available on the internet for you. Many more things than that. Okay? So my suggestion to you is take science seriously, take our literature seriously. நான் பொன்னியின் செல்வன் மட்டும் படிக்கல. நான் இந்த என்னது அவர் எழுதியிருக்கிற ஒரு 6-7 நாவல் நிறைய படிச்சிருக்கேன். சாண்டில்யனுடைய 10-15 நாவல் படிச்சிருக்கேன். தமிழ் லிட்ரேச்சர் is very interesting. Science is very interesting. Tamil philosophy is very interesting. Therefore, I think you should get excited reading, learning multiple things. Science ஒரு இடத்துல படிக்க வேண்டியது புரிஞ்சிக்க வேண்டியது முக்கியம். Solve many problems. And I don't know whether I will meet you again during this course, but I want all of you to succeed in whatever you want to do. I won't be given the first lesson in NMR, what I call as one lecture, 2 lectures in my class, regular class. I give to my class about 25 lectures like this in the MSCBR. So I can't do all of them in this time. So I would like you to read these lectures. I'll send you this lecture by electronic mail, and I'll send you some 8 or 10 problems along with that. Try to do all of them. You'll take the first step that you are afraid to take of trying to understand the mathematics. Mathematics of NMR is important, not just for mathematicians, not for chemists, but it's important, not for physicists, but it's important for chemists to do useful contribution. Okay? I wish you all the best. Somebody passed my time. Oh, sorry, I still have about 10 minutes. So if you have any questions. If not, one last lesson. Okay? I still have about 10, so I didn't realize. My time is half an hour. I'm 11.5 hours behind you. I'm in Alberta, Edmonton, Canada, which is almost diametrically opposite to India now on the earth. So you have to come around. I'm on the other side of the earth. ஒரு 12 மணி நேரம் தான் எக்ஸாக்டா யூஆர் வே 12 மணி நேரம் இது 11 மணி நேரம். So my time here is 11:15 in the night, previous night. You are on the 9th, I'm still on the 8th, Sunday 8th. So let me just give you one quick lesson in the second one about what is resonance. That I want to tell you. More lectures. I'll go to the lecture and then share. Yeah, let me share the screen. Oh, you're able to see the screen? So the dynamics of the nuclear magnetic spins, magnetic resonance, the spins in a magnetic field. The equations are very long, but I will just give you the basic idea. Okay? So what happens is you put a magnetic field H dot and the direction of the field as Z. Okay? Then angular momentum change is given by a classical formula. Namely, you remember spin has a magnetic moment mu. The rate of change of angular momentum d by dt of J is the torque. This is called the torque. The torque is the cross product of the vector magnetic moment and the magnetic field. The vector magnetic moment is gamma times the angular momentum. Therefore, the rate of change of angular momentum J is gamma J instead of mu cross H. The cross product of a vector, you remember, is usually written using a determinant. So J has components Jx, Jy, Jz. H has only one component, z-axis, H0. So it is 0, 0. So if you write the differential equation dJ by dt as gamma J cross H, you can take the cross product. X into Jy H0 minus Y into Jx H0 plus Z into 0, 0. So dJx by dt, if you take the X component here, dJ by dt is given by Jx, Jy, and Jz because they're all vectors, x, y, z vectors. So the x component dJx by dt is the x component here, which is Jy, y0, omega naught. The y component dJy, if you look at it, is the y component here minus Jx omega naught. Take the z component dJx by dt, there is no z component here. dJz by dt is 0. Okay? Therefore, you see that the angular momentum satisfies this relation in the presence of the magnetic field. Omega naught has the magnetic field. It's gamma H naught. So the gyromagnetic ratio takes the magnetic field. So dJx by dt is omega naught Jy. dJy by dt is minus omega naught Jx. dJz by dt is 0. If you solve this equation, you get Jx of t is cosine omega naught t plus sine omega naught t, and Jy of t you get minus sine omega naught t plus epsilon. A and B are constants. And since dJz by dt is 0, Jz is a constant. Therefore, the solution suggests that the angular momentum J recesses about the z-axis so that the z component remains the same. Z component doesn't change, it's constant. the x and y component oscillate. They go from cosine omega t. So let me just, they go from the z component. The magnetic moment is like this in the field. It's like this one. Its z component is this. That doesn't change. But the spin precesses around the magnetic field, so that the x component at the bottom and the y component, they are following the precession, the average of x and y. So in the magnetic field, a quantum magnet does not stay static. It is precessing about the magnetic field. So net x component or y component. This precession is called Larmor precession. This precession, you can see that. So the Jz is this component of J of t. The x and y are perpendicular plane to the Jz. And the x and y rotate. And the precessional frequency is omega naught by 2 pi, which is naught. And that is the Larmor frequency, nu naught. So now, if you add a radio frequency magnetic field in this direction, what happens is the spins which is rotating in this direction, spin a half, can absorb the energy and then come down to the minus direction. And the resonance absorption can happen. So the spins can flip their orientation from plus to minus or minus to plus. And the field which causes this flip is the radio frequency magnetic field in the x direction, which is oscillating cosine omega naught t. You can see that. The radio frequency field cosine omega naught t. Okay. Now what it does is that it creates, let me not do any of this, it creates the flipping of the spin one half from the positive z to the negative z direction. Felix Bloch wanted to model this whole problem, and he introduced a model called the phenomenological model for relaxation of spins in the magnetic field. And I'll give you only the final equations that Felix Bloch gave. Felix Bloch answered the following. Suppose there is no magnetic field. The spin moment is magnetic moment is zero. There is no magnetization. But as you put the field on, the magnetization grows steadily and reaches a constant value. And that is the diamagnetic magnetic moment M naught. Okay. Maximum. But the maximum will be reached only after a long time, but almost here, which is the finite time. So this is called the spins relaxing in the magnetic field to reach a magnetization. So this was modeled by Felix Bloch using a simple first order differential equation. The rate of change of mz with respect to t as the difference between the maximum m naught and any value of mz at any given time. And there is a relaxation time constant called a T1. So if you remember, this is like a concentration. 1 by T is like a rate constant. So you can see that the rate constant is 1 by T1, like first order rate constants. The rate constant has a dimension of second inverse. So 1 by T1. So T1 is called the spin that is relaxation constant. If K is very large, 1 by T1 is very large, or T1 is very small. If K is very small, first order rate constant. If K is very small, 1 by T1 is K, so T1 is very large. What it means is that if the relaxation time is short, the spins reach the maximum very quickly here, this way. If the relaxation time is very long, the spins take a long time to reach the magnetization in a magnetic field. So solids have very large relaxation times. But when you put a magnetic field in a solid, the magnetization takes a long time to set up. And When you do resonance experiment, the magnetization goes to 0. And then it again builds up. So it takes a very, very long time for the cycle to continue. And that was one reason why resonance experiments failed in solids when they were done in the early 1930s. Felix Bloch took a liquid sample. And in the liquid sample, the relaxation time T1 is very short. Therefore, the moment you put the field, the spins go cook. Very quickly, they go to the magnetization. They achieve the magnetization. And when you turn off the field, very quickly they go back to 0 magnetization. So the speed, relaxation time, was responsible for the success of some of the experiments in the early days of magnetic resonance. This model, which was extended by Felix Bloch, including radio frequency fields, is called a very famous relaxation model in NMR. And even today, many experimentalists use this concept to study spin lattice relaxation time and an associated quantity called the spin relaxation time. And they report these as fundamental properties. Okay? So with all of these things, there is a lot more to learn, and there is a lot more to understand in the theory of NMR. And I would not go any further than this. Okay? But we'll tell you that like this, there is a whole lot of fundamental phenomena in magnetic resonance that you should be very familiar with. And I hope that you will take the time to pick up a very elementary book which talks about all these methods. And Professor Dr. Bhaskar, who is our NMR chief scientist in the department, he will probably meet you sometime. Please talk to him and ask him about a special lecture on the experimental methods of NMR. He will also give a very quick experimental summary of the various NMR methods. And I hope you learn doing that problem, okay, doing that process. And my lectures, the ones I did yesterday and the ones I did today, I'll send you in a day to Professor Anderson, and he will put it up in some common area for you to copy and download. And if you have any questions, you all have my email ID and you have my contact details from the institute you take it. And please let me. I wish you all the very best. And if I have time and if there is a slot, I will join you towards the end to study something about vibrational spectroscopy and about rotation spectroscopy. But I don't know how much time you have, and you are also very tight, very busy, trying to learn many things in 15 days. State government is spending a lot of money on you. So please take this opportunity and learn. Best wishes to all of you. Okay? Thank you.
Swayam Prabha, Digital India, Educated India.